Hey, what's up, people? Okay, so we're back. We're back. Oh, it's late. Yeah, it's late. Went to the gym. Went to the gym. I ran 5 miles, baby. No breaks. No breaks. 6.5 miles per hour. 43 minutes. Pretty good. It's a pretty good workout, honestly. Just cardio, obviously. And okay, so it was 46 minutes or something anyway. I can't remember. 45 minutes, 46, whatever. 5 miles, baby. And I had a terrible stomach ache. I don't know. For a little while. I was gonna stream earlier, but like my stomach was hurting like bad. It doesn't really happen often. Anyway, so let us go ahead and pick up where we left off, which is where we were. Okay, so yeah, we finally made the decision, right? We finally decided that we're gonna go with SQL. We did the benchmarking, we tailored the benchmark, we verified the benchmarks, we made sure that it was accurate. I didn't use time it like I said I was gonna do, but I mean, like, the results are so, like, it's not even close. We finally decided that it's so much faster. The okay, so the SQLite was so much faster than the pickle option, and you know, it was really fast, super fast, so fast. It's so fast that honestly, matter of fact, let's run this one more time real quick. And what I want to do, I want to actually see. We're not worried about pickle anymore. I'm not gonna do pickle. We're not worried about shelve. Well, shelve though is secure like a database, right? Because it uses some like database-like technology. So I don't know. Maybe we will take a glimpse into shelve. But let's run this test again. And this is with WAL enabled, and that is write ahead logging, which is basically like I can't really explain it. I learned about it, but I can't really explain it. But anyway, so using as you can see right here, both of them have write ahead logging, and that would be the batch and the single update, single write version benchmark. Yeah, so they both have that enabled. So that's not what's skewing the results. Let us go back to our old GPTs and okay, so we're here. If you wanted to speed up, okay, let's go back up a little bit. It's very risky because it disables fsync calls, meaning SQLite does not ensure the data is physically in the disk before considering a transaction committed. Okay, we're gone. We're back again. Get a piece of gum here. And apparently we're reconnected. But so I'm learning. This is really what's happening here. This is just a big class. This is a class learning about databases and different, types of databases, or save file systems, backup systems, whatever you want to call it. So I want to understand this a little bit further. I looked at it some, but let's also open up Claude because I had it in Claude. I can't remember exactly. You know, I was here, I was there. I was in various different locations, and okay, so this is the most recent one, I think. Let's go skim back over this. Okay, so we were wondering why this was so much faster. This one gets 6,900 right per second. The Cape, this one gets 678 right per second. It's 10 times faster. I was like, why is that 10 times faster? Um, well, and that is due to the fact that one of them, namely the batch state, uses this line right here, which says self-con execute begin transaction. So this is critical right here. This begin transaction thing, it is what is the only difference between the batch write and the non-batch write mode currently, because we changed the batch size to 1. So since the batch size is 1, it functions exactly the same as a singular as this one, the SQLite individual, but it's 10 times slower, or 10 times faster than the individual. So why would it be 10 times faster if everything's the same? The only thing different is this begin transaction, and it told me that the performance difference is due to the overhead associated with committing a transaction in SQLite. So it's not committing every 10 inserts significantly faster. Each commit requires ensuring that all changes are safe through the disk, which also no. That's not right. Actually, we actually clarified this. It's not actually the difference in commit because the batch size was only 1. So this is null. We don't need to worry about this. See, this is how you can trick AI. Like, I tricked it into, well, I didn't trick it per se, but AI is not perfect. It didn't like because I didn't give it the context. How would it know? So it didn't make a mistake. It was just user error. But anyway, you have to prompt properly if you want to get all the pertinent information. If you don't prompt properly, then you're not going to get the answer that you're really looking for. So wall mode versus default journal mode. If you're using SQLite's default rollback journal mode, every transaction, even a single insert followed by a commit, requires writing to a journal file, modifying the database, and syncing changes to disk. In contrast, using write-ahead logging, okay, so this is what we're talking about, WAL, write-ahead logging mode can improve performance since commits don't require as many costly disk syncs. Commits don't require as many costly disk syncs. So it kind of like, as far as I understand it, it optimizes the, basically creates like a queue of commits, and then will sync to the disk less frequently, which I guess is the most costly task as far as performance. SQLite locks the database during transactions to maintain if each insert SQLite has to, yeah, we're not worried about that. Let's go optimization. We're running this to improve performance further. Blah blah blah. Okay, so then when you use wall mode, running pragma journal mode can significantly reduce commit overhead. Disable synchronous writes. Running pragma synchronous off removes fsync operations, making commits nearly instant, but at the risk of data corruption on crashes. Okay, so this is what I wanted to ask you about. Does this imply that it could corrupt the entire DB, or just cause immediate short term data loss. So then we have, yeah, disable synchronous writes, which I don't really know what that means. Explain synchronous writes a bit further. I would think synchronous writes would be like more. Synchronous means like at the same time, like, right? So I'm thinking synchronous is more. And then we can use execute many for bulk inserts. If applicable, so execute many can speed up inserts. Okay. And then we asked about, do we have to use Pragma Journal one time? Great, I remember that. Okay, so then how risky is synchronous off? Setting Pragma synchronous off is very risky because it disables fsync calls, meaning SQLite does not ensure the data is physically written to a disk before considering a transaction committed. So that means you could commit, but it technically isn't committed. Yeah. So power loss system crash. If the system crashes before the data is fully written to disk, the database file may become corrupt, potentially making recovery difficult. A transaction might appear committed when be lost if the OS hasn't actually written the data to disk yet. If using WM mode, the risk is slightly lower because SQLite keeps write-ahead logs, reducing the chances of full corruption of these recent transactions if they haven't been checkpointed. So if an interruption occurs, however, the database file may be left in an inconsistent state. Yeah, we don't want that, right? We don't want that. We don't want that. We do want security. So, like, you know, speed versus security. It's already fast enough. So, I don't think... It says that this is very risky. So I'm going to just go ahead and say it's probably very risky. We're probably not going to use synchronous off. And fsync is what makes it so secure, as far if I understand it. So, stable alternative: if you want to speed up writes without extreme risk, consider these options. Fragment equals normal. This is default in wall mode. It avoids excessive fsync calls, but maintains reasonable safety. And then trade-off is faster than full, but less safe than full in case of crashes. Okay, yeah, I'm like a moderately risky kind of guy. I'm not too risky, so yeah, we'll go with that, which is the default in wall mode. So it should already be set to this. I guess it would be cool to, you know, have it executed just in case, like, it wasn't, you know, actually happening, even though it says it's a default. I guess we could probably return the synchronous, just like we do cursor execute pragma journal mode. We could probably do pragma synchronous. You dig? And then we could, that would probably check the synchronous. Yeah, okay. Yeah, so we're gonna add this to the, oh, we'll just copy this entire little thing. And then we'll go to the single, which should be above. Yeah, right here. That's it. Wait. Okay, yeah, because we only do this once. Oh, it looks like we did it twice there. Okay, and then let's comment this out, and let's see what we get for this. Yeah. Okay. Yeah. So we have cursor execute pragma journal mode, fetch 1, execute pragma synchronous, fetch 1 again, and then up here we should have the exact same thing. Cursor execute pragma journal mode, fetch 1, pragma synchronous, fetch 1. There we go. Cool. Okay, so let's test this. Well, first of all, let's comment out the normal layer. And now this is going to be run. And okay, so we get, oh, why does it show 2? Well, interesting. Okay, so then we have a pragma synchronous. So, but I'm trying to figure out this. Why does this return 2 instead of full / normal? And it's going to say the pragma synchronous statement returns an integer value instead of a string. Numeric values correspond to the different synchronous modes. So value 0 is off, no syncs, fastest but unsafe. 1 normal, some syncs, moderate safety. 2 is full sync after each commit, safest. And then 3 is extra, like full but with an extra sync before writes. So when your code prints 2, it means the synchronous mode is set to full. Ah. So that is not what we want. Alright, so let's read this a little more. Oh, which one? Okay, so we said not that. Where is it? Where it is? Where it is? Here it is. This implies that it could corrupt the entire database, or just cause media short-term data loss. Okay, so let's read this. How SQLite synchronous writes work. SQLite writes data to disk asynchronously by default, meaning data is first written to an in-memory cache before it is physically written to disk. Okay, so it is first written to in-memory, and then it is physically written to the disk. The synchronous setting controls how aggressively SQLite ensures that committed transactions are actually written to persistent storage. So it's basically like physical write frequency. When a transaction is committed, SQLite typically calls fsync or equivalent to force the operating system to flush any buffered data to disk. This ensures durability. If a crash or power failure occurs after a commit, the data is already safely written and won't be lost or corrupted. Okay, right. I mean, I'm just concerned about corruption of the file. If the file is fine, then like, and there's just a little piece of it that's corrupted, I don't care. If it's like 10 times faster, I'm going to go with the 10 times faster one, because that to me is security in and of itself. If it's 10 times faster, it's like if you have a guy who's running from one side of the street to the other, and cars come every so often and he could get hit by the car. I'm like, would I rather a guy that can run like average speed and checks for cars, like, well, I guess it's not the best example, or would I rather have like the Flash, and the Flash can literally, like, he goes so fast that like as long as the car is not in his direct path, it can't even hit him. You know what I mean? So like basically, the car is the power crash, and the runner is the it's like the right or whatever you want to call it, like the transaction, whatever you want to call it, the save. So I would feel like, you know, that would be preferable, even better, if that's a accurate analogy. We have when it, durability, data safety. Pragma synchronous levels and their effects. SQLite provides 3 levels of synchronous settings: full, safest, lowest, default, and delete. Ensures every transaction is fully written and synced to disk before returning control to the application. System crashes, committed data is guaranteed to be intact. Downside: significant performance overhead due to frequent fsync calls. Balanced is normal, default in WAL mode. Syncs data less aggressively, allowing some transactions to be buffered. Syncs data less aggressively, allowing some transactions to be buffered before syncing. Less durable than full, but still relatively safe. If system crashes, recent transactions may be lost, but the database itself will remain encrypted. And that I don't care about. I don't care about that. But if we do off, which is fastest, riskiest, it completely disables fsync calls. SQLite writes data to the OS cache, but does not force an immediate flush to the disk. If the OS crashes before, oops, forgot to set our, I forgot to start our timer. I actually did set the timer, but I didn't start it. So we're 22 in, which means we got 40, what is it? 46. 46, there we go. So it's, clock's ticking. Okay, so off is fastest, riskiest, it's dangerous, complete divs fsync calls, but does not force an immediate flush to disk. If the OS crashes before it flushes the cache, if the OS crashes before it flushes the cache, any committed transactions that weren't actually written to the disk will be lost. Any committed transactions that weren't actually written to the disk will be lost. In some cases, it can leave the entire database file corrupted if only parts of the data were written before the crash. It does off risk corrupting. It depends on the journal mode. In write-ahead logging mode, the risk of complete database corruption is lower because writes go to a separate WAL file first, and the main database file remains mostly untouched. If a crash occurs, unflushed transactions may be lost, but the database is most likely to remain intact. Worst case, the WAL file might be lost, meaning you lose reads and writes, but you can still open the database. In delete or truncate mode, default journal mode, the risk is much higher because SQLite modifies the main database file directly. If a failure occurs mid-write, you can end up with a partially written database file, leading to corruption. Okay, so in this one, with WAL mode enabled, synchronous actually could be off and you still wouldn't lose the database. You still wouldn't corrupt the database. Let's go to a separate area file database. Okay, so with WAL enabled and the, let's see, with WAL enabled and equals off for sync, total DB corruption is virtually impossible, since it writes to WAL first, and then we'll call fsync at a later time, ensuring a batch from the WAL gets written to disk. You should care about data safety, not using data cost per data corruption. If you want balance speed, safety, synchronous, or self-performs. Statement return is an integer value instead of string. Gotcha. It's totally big option. Virtually yes, with caveats. When WL mode is enabled in prog, when synchronous offset, the main database file is never directly modified. Right, so instead, all changes to the significantly the chance of total database corruption because this file stays mostly safe. SQLite only modifies the main DB file when a checkpoint occurs. DB. Even if a crash happens before the wall is checkpointed, DB remains in its last consistent state. If a crash happens before the wall is checkpointed, DB remains in its last consistent state. Crash before checkpoint equals lost transactions, not corruption. Gotcha. Crash during checkpoint equals partial disk write. The biggest risk is if a crash happens during a checkpoint when SQLite is copying data from WL to main DB. Since synchronous off disables fsync, thus might not actually flush the writes to disk before a crash. However, even in this case, SQLite has some recovery mechanisms, and the worst case scenario is usually a WAL rollback rather than full. It's extremely unlikely but not impossible. Most likely failure is WAL loss, losing recent writes. If you want maximum state to consider using 10% of off. Okay, so data from WAL to main DB. So this would happen so does this consist of an fsync? Is this a vulnerability for essentially all SQLs and transactions? Yes, when SQLite checkpoints the wall file, merging its contents into the main DB, it performs an fsync to ensure durability. However, whether this happens in the pragma synchronous setting, main DB checkpointing include an fsync. Yes, when SQLite checkpoints the wall file. Fsync versus OS eventual disk flush. I don't understand the difference here. What do you mean that the OS will eventually flush it? SQLite is not collapsing during the checkpoints, meaning the OS decides when to flush data to disk. If a crash happens mid-checkpoint, the database could end up in a partially written state, leading to possible corruption. Yes, all database systems that use transaction logs or WL-like mechanisms have some risk during log checkpoints. The key difference comes down to how each system handles syncing and crash recovery. SQLite wall mode checkpoint merges wall to main DB with fsync depending on synchronous settings. Synchronous off, there's a risk of incomplete writes leading to corruption. PostgreSQL uses a write-ahead log but keeps committed transactions durable using fsync or group commits. Less risk of corruption because it has stronger crash recovery mechanisms than SQLite. And then MySQL NODB uses double write buffering, meaning dirty pages are written twice, once to a special buffer, then to the main table. This helps prevent corruption even if a crash occurs mid-write. Other embedded databases, LMDB, many log structured, checkpoint. Most handle things carefully to minimize corruption risk. Use WL mode for high rate writes. Set synchronous normal instead of off. Okay, increase wall checkpoint threshold to delay merging. Increase wall checkpoint threshold to delay merging. Oh, because then it would happen less often, so you'd have less opportunity for data loss. But that's kind of counterintuitive because then you would have less save frequency. Manually trigger checkpoints at safe intervals. Checkpoint. Manually trigger checkpoints at safe intervals. Would you? Okay. All right. I'm with you here. We're probably just gonna do normal. We're probably gonna do we're gonna do synchronous normal because it's set to full, and we can change it to normal. Okay, then we have fsync versus OS eventually. What's the difference? When a program writes data to a file like a SQLite database, the data does not immediately go to disk. Instead, the operating system buffers the write in memory for performance reasons. Okay, out fsync. The program writes to a file. The OS typically pushes the data in RAM instead of writing it immediately to the physical disk. The OS decides when to flush this data to disk. Decides when to flush this data disk based on factors like memory pressure. If the system crashes before the OS writes data to this data is lost even if the program thinks the write was done. Stores this data in a buffer by 30 seconds. Is low. With fsync immediate flush, when a program calls fsync, it forces OS to flush all the writes for that file immediately to the physical disk. The function is not returned until the data is safely stored on non-volatile storage. This guarantees that a crash after fsync completes won't lose that data. Okay. This thing's not called SQLite commits may remain disk. If pragma synchronous is equal to off, SQLite never forces an fsync. Pragma synchronous off, SQLite never forces an fsync. Rely on the OS to decide when to flush DB. If the OS crashes before the flush happens, you use transaction that SQLite write. Imagine writing something in a notebook without fsync. You write notes, but your notebook is in your backpack. If you lose your backpack, with fsync, you immediately move the notebook to a fireproof safe, ensuring it's permanently stored. Gotcha. Okay. So we'll probably just use normal because then we'll say, what was the other one? Begin. Tell me about begin transaction. It's way faster. Why is begin transaction so much faster in SQLite? By default, SQLite automatically wraps every individual insert, update, delete statement inside its own transaction. This means the database does a full transaction cycle for each write. Each transaction cycle includes journal writes, file syncs, and commit overhead. This does a full transaction cycle for each write. Journal writes, file sync, and commit overhead. If private synchronous is equal to full, SQLite will fsync after every statement. Using begin transaction. Multiple writes into a single transaction. Without begin transaction, slow. For I in range of 10. Cursor execute, insert into my table values, and then con commit. Starts the transaction, writes to WL fsync to ensure durability, commit the transaction for every single insert. Commit triggers disk writes plus fsync, which is expensive. Transaction is fast. Begin transaction for I in range of 10. Then we insert into these, then we would execute commit. What happens now? Transactions start. Happen in memory or WAL. Single commit writes everything at once. And then only one fsync happens. Much faster because journal writes and fsync occur once. Not 10 times. Okay. Okay, no. Yeah, we're gonna look at the benchmark because it told me something different before. So now to enable pragma-synchronous set to normal. Okay. So now it should return not it should return right? So we do have 1 and then WAL, so it's in WAL mode and it's also synchronous is set to normal. And let's see what the results are here. We have damn. Hold up. Did I use begin transaction? No, I didn't. I didn't even use begin transaction in the single version for SQLite state. But it actually, oh no. Oh shit. 55,575. Damn, son. Okay, so SQLite individual is really fast now with so with synchronous set to full. Run it again. It's gonna go from 57 down to just 7,000. So it's like 6 times slower. Something like that. But do we need it to be that fast? I don't think we do. Like, that's ridiculously fast, you know? That's insane. That's bonkers. But as long as they say that it's safe enough, we'll roll with the pragma synchronous normal. You know? Just because I do love performance. I like the idea of having really good performance. I love that. I just like it. It makes me. So I think we'll leave it, and I mean the batching thing. I just don't think we need to do the batch commit thing. I think this is fine. I just wonder, you know, like how often are we actually getting this data written? You know, I'm guessing it uses RAM to pass it off to the disk in like a smart streamlined way. So it's probably actually not that much like slower, you know what I mean? It's probably almost as fast, quote or slash secure, but it's just like optimized in such a way that it's batching it in its own way to the RAM before it hits the disk, and then it's going all in at once in like a block instead of like little do 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 do. It's more like boo boo boo. You know what I mean? Like I'm thinking of it in that way. So yeah, I think yeah, we'll go with the pragma synchronous normal and with WL mode. So let's just disable WL mode and let's see what we get here. Okay, so WAL mode doesn't actually give us our benefits. So really, so 5848, and then with WAL enabled, it was. Okay, that's not right. Hold up. Okay, so we got journal mode, WAL. Well, it might already still be set to WAL. No, because it would say, and it does say WAL because it's already been set. So it's still in WAL. So if we delete the file though, then it won't be in WAL anymore. So we go down here, we delete this, and then we delete the full state pickle. Partial state, yeah, we delete that too. That doesn't really matter. We're not worried about pickle. That was the pickle stuff, but it's all good. Okay, so now it's in delete mode, and go. So WAL disabled, but synchronous set to normal instead of full gives us SQLite individual benchmark of 221, which is way slow compared to. Now let's disable synchronous normal and let's rerun it. So this time it's in delete mode, and then it sets a full, which is the 2, right? 2 represents full, and now it's down even lower to 168. So it went from 222 to 168. So and that was changing synchronous. So synchronous does have a big effect. It went from 168 to 222. That's like a, you know what, I don't know. That's like a 40% decrease. That's like a pretty big decrease in speed. But I don't necessarily know it's a pure percentage thing. Because let's rerun it. So it should be back up to like 220-ish. Okay. And this is just synchronous. Yeah, so it's back up to 220. And then we have, what the fuck is this? Spider, a little bug. Okay, and then now let's re-enable WAL without synchronous set to normal, and let's see what we get. So now it's WAL, but it's set to full. We're getting 754. So we went from what, from 220 to 754. And now, so WAL mode is the real winner here. WAL is what really makes the big difference. But then if we set synchronous to normal, actually scratch that. Synchronous normal is even more influential based on this test. Let's do this again. Synchronous back to full. You get 752. Okay. Oh, so it is like a percentage thing. So 752 without it, and then with it, we get almost 10x, like 8x. Now, if we do WAL, disabled, we get 5212, but it's already in WAL. We have to delete it for it to not be in WAL. So if we delete, which one is it? No, we don't worry about those. We just worry about the DB. So it's just this one. There we go. All right, so let's rerun it. And it's not in WAL mode, but it has synchronous set to normal. U214. Then you set it back to WAL. And it's going to be out of this world. Now it's at 4757. But then if you set synchronous, so they work in tandem with each other. It's like fucking it's like having a turbocharger and then having NOS. Like one of them allows you, you know, like you can have NOS but without a turbo or whatever, like it's not gonna really help you or some shit, you know, sort of. Is not how it works. But then like if you have a turbo without NOS, it's really good, but then you have a turbo with NOS, it's like, whoa, you know, it's crazy. Yeah, so this would be like having the turbo wall mode, and then when we do the synchronous to normal, this is like NOS. There we go. It goes up from 744 to fucking 56. But if we drop WAL with normal, try this again. If we drop WAL with normal, yeah, then it's only 221. So, and then if you have WAL without normal synchronous, it's pretty good. It goes up from 200 to 770, but then when you enable sync normal, it goes up from 770 to like fucking 6,000. Nuts. Okay, so those two things together make a huge difference. I wanted to ask it about so begin transaction. Remember we were talking about this? So we have, let's see, begin transaction. It said it was actually more than meets the eye. Namely, it wasn't just like it wasn't just like this little answer it gave me based on what I read earlier is not actually the complete truth. It's emphasizing here that it's only doing one commit per 10 inserts, but then remember we prompted about the fact that we reduced the insert to commit ratio back to 1-to-1. So like even with begin transaction and a 1 insert to 1 write versus non-begin transaction 1 insert to 1 commit. I said right before, but I mean commit. Basically, the only difference is one of them has begin transaction enabled, the other one doesn't use begin transaction. The one that uses begin transaction, even though it's still 1-to-1 insert commit, you still get like 10 times faster performance with with begin transaction. So let's like read that a little bit. It should be this latest thing. It was one of the last. Yeah, here we go. All right. Let's see. How dangerous is the seldom we need. Let's go back up. It said we didn't really need it. We're gonna try to. Okay, here we go. This was. It doesn't immediately write changes to disk. So begin transaction. It doesn't immediately write changes to disk. Changes are first recorded in memory. Disk writes are postponed until commit. SQLite can optimize and group multiple writes. Reduce the number of costly disk synchronization operations. This means fewer system calls, less overhead per write. Fewer system calls, less overhead per write, more efficient use of disk I/O. Yeah, and then I clarified. But even with a batch size of one data change per commit, just like the first option, it's still way faster. This means it's not actually committing each data change like the first option, even though commit would run each time just like the first option. I still don't understand why begin transaction makes it so much faster despite still committing each 1x data change. And it says disk synchronization means forcing the operating system to write data from memory. Disk synchronization means forcing the operating system to write data from memory buffers to physical disk storage. It's a slow operation because must wait for physical disk write to complete, requires mechanical disk movement. OS must ensure data is safely stored. The key is that begin transaction changes how SQLite handles the writes, even with batch size is equal to 1. So this is what I was talking about. Without begin transaction, it will write the data, force sync to disk, wait for completion, and then continue. And then with begin transaction, it will write the data, store in SQLite's WAL file, and then continue immediately. See, and I'm confused about this. I don't know if it is getting this right because begin transaction, what it seem to say, it seems to be saying begin transaction is doing the same thing that enabling WAL mode does. Even though both commit after you change, the second approach uses WAL file more efficiently, defers actual disk synchronization, allows you to optimize write patterns, reduces waiting for physical disk operations. It's still committing each change but doing it more efficiently through transaction management and WAL optimization. So the WAL file is separate from the main database. When using WAL mode, it contains the core data. db-wal contains recent changes. Changes are first written to WAL file very fast, and then they're later merged into db file. Checkpoint operation improved write performance, allows concurrent reads while writing. Is begin transaction only associated with WAL mode? No, begin transaction works with any SQLite journal mode. WAL delete truncate is a separate feature that manages how changes are written to the database, regardless of which journaling system is being used. It's a separate feature that manages how changes are written to the database, regardless of which journaling system is being used. Okay, so, and this is basically the final. Let's see. Without begin transaction, write data, force sync to disk, wait for completion, continue, write data, store in SQLite. So WAL file, continue immediately. Explain this same scenario using the same language example, but for WAL instead of begin transaction. Okay, so say write data, write to main DB file, force disk to sync with WAL mode, append to WAL file. Okay, so tell me in this manner how begin transaction would work with WAL enabled and without WAL enabled. And this will clarify my final layers of confusion with this WAL versus transaction. With wall plus begin transaction, you will write data, store in memory, batch write to WAL file at commit. Stored in memory, batch write to wall file at commit. And then continue immediately. And then without wall plus begin transaction equals write data, store in memory, batch write to wall file at commit. Continue immediately. Without wall plus begin transaction, write data, store in memory, batch write to rollback journal, then main DB at commit. Key is that begin transaction with wall still gets the speed benefit of WAL's quick appending, while without wall it has to still gets the speed benefit of wall's quick appending, while without wall it has to wait for the traditional journaling and disk sync even though it's batching the writes. Both use memory buffering from begin transaction, but WAL mode makes the eventual commit faster by using the append only WAL file instead of having to write to both a rollback journal and the main DB file. Frying my brain here a little bit, but this is part of learning. It's like working out really hard. When you work out really hard, you're like straining and like, I can do this, maybe I can't, maybe I can, and then you're like, wow, I actually did that shit. And it's similar to learning something new, except it's with your brain, you know. So it's like stressful. A little bit of caffeine there. Okay. The final. Let me create a clear comparison of wall and begin transaction. So wall is write ahead logging. Its purpose is for journaling made. They serve different purposes but can be used together for maximum performance. Wall handles how changes are written to disk. Handles how changes are written to disk. Begin transaction handles how changes are grouped together. Combined, they give you both efficient disk writing and operation batching. So WAL is purely for writing to the disk. It makes that faster. It's like memory versus SSD. WAL is like memory, and then the disk is like the SSD. It's like just faster. And then it batches them, and then it's like bam. Without WAL, it's just going straight to the DB, which is it's going straight to the disk. It's a little slower. Begin transaction handles how changes are grouped together. I don't really completely understand this. Changes are grouped together. Changes combined to give you. So begin transaction is a transaction. Let's see. Transaction management mechanism Why did it make it to where I have to scroll to read this? When active, persistent database setting. Temporarily until commit rollback. Okay. Write process appends changes to separate WAL file. A write process appends changes to separate WAL file. Buffers changes in memory. It buffers the changes. That's the key takeaway. Is begin transaction buffers the changes in memory. Performance gain from batching multiple operations together using the memory. Concurrency might block other connections. Memory usage holds all changes in memory. Risk of losing uncommitted changes. Recovery, manual rollback if needed. Disk usage, no additional files. Uses existing journal. No additional files. Use case, high frequency write batching. So begin transaction stores batched changes in memory even though you might have executed .commit already. They aren't committed to the disk but are in memory instead. And this allows it to batch changes faster. It's not quite correct. When you execute commit, the changes are written to disk. Here's what happens with begin transaction. Changes are stored in memory between begin and commit. When you call commit, those memory changes are written to disk. The performance gain comes from batching multiple changes into a single commit. So it's not that commits are held in memory. Rather, changes are held in memory until commit. They're written to disk more efficiently as a batch. The speedup comes from reducing the number of disk. So even if we have, I'm going to ask this again, begin transaction used, and we have one data insertion per commit. But why do when we have begin transaction enabled and we have one data insertion per commit versus it disabled and one data insertion per commit, the begin transaction method is like 8 to 10x faster. The key is that begin transaction changes how the commit happens, even for single inserts. Without begin transaction, the write starts, create the rollback journal, writes to journal, writes to database, sync to disk, delete journal, each commit does all these steps. With begin transaction, the transaction starts, the write happens, commit bundles the journal and write operations more efficiently. Commit bundles the journal and write operations more efficiently. Using memory instead of the disk, like so SQLite can optimize the entire operation. So even though you're still doing one write per commit, begin transaction allows SQLite to optimize the whole write journal sync process. It's not about batching multiple writes, it's about making each individual write more efficient by telling SQLite this is a transaction, so it can handle all the under the hood operations more efficiently. Think of it like packing a box. Without begin transaction, you're opening and closing the box for each item. With begin transaction, you're telling SQLite, I'm going to put something in this box so I can optimize how it handles the packing process, even if you're only putting in one item. There it is. What a nightmare. What a nightmare it is to learn something new and to not be able to actually make progress on what you're doing and just learning. All the progress is up here, and none of it is here on the screen. Isn't that sad? It is. But now I have a very solid understanding of how this works with the journal, the database, and etc., etc. I am of the understanding now. So let's just see the final test. So we have journal mode, wall, synchronous, normal. Now what we're gonna do is, where is it? We have the magical begin transaction. See? Currently, with begin transaction only on the batch version, we get 38,476 writes per second versus 5,500 writes per second, which is what, 6 times slower? It is, 1/6 as fast. So therefore, yeah, it's 1/6 as fast, and the only difference is the begin transaction, or at least that's the theory. So if we add in begin transaction here, and this, when do we put this? We put this prior to the execute insert, so right here. Now let's see if this makes a difference. Well, it didn't make that much of a difference. What the fuck are we talking about here? Someone has lied to me. Someone has lied to me, man. Lied to me. This is not right. Wait a second. I don't care anymore. I don't care why this one is showing 50,000 and the other one is 62 and there's no difference. I don't care. I don't care. I really don't. I just want to see something real quick. All right. I don't care. Let's do this. We're gonna make them the same, and I'm telling you, if one of them's still faster, it's gonna be pissed off because there's that means there's something wrong with the benchmark itself. Saying that means there's something going on with the benchmark that's skewing this. There we go. Now they're the same. So there's something wrong. Let's see. That would begin. Fucking stupid. So actually, the AI was right. I convinced it that it was wrong, but it wasn't wrong. $53.63. 53.63. Now let's re-enable begin. And then run it. 53.63. 53.60. 52.62. 50.68. $51.63. Disable it. Or disable. Yeah, it's virtually the same. But let's do 10 without it. So we're looking at 51.67. Write these down. I'll just write them down. Just write it wherever. It doesn't matter. Here. So we're gonna say 48, 78, 71.96. Okay. Now we're gonna do this again. We're gonna do this 10 times, real quick. So let's go back. We'll just do 5, 2. All right. So this one is 59.65. So let's say 59.65. All right. Next one. 162. So 51.62. All right. This is number 4. This is without begin transaction. 66. Say 51 and 66. Okay. All right. That's the last one. That's 4, right? Yeah. This will be number 5. And we get 44.71. So that one's a little slow for whatever reason. All right. Now let's do with now they're both enabled. Let's look at it now. 61.67. Let's do it again. $57.68. 52.62. Again. 5,064. Okay, there we go. That was 4. We'll do the last one. All right, now we're gonna do the maths and divide, and I'm pretty sure there's basically no difference. 56 and 59. All right. So now we're gonna do calculator. We're gonna whoa, didn't mean to do that. So let's do 4878 plus 59 plus 5900 plus 5100 plus 5100 plus 4400. Okay, divided by 5, that gives us 5075. 5075, and we'll do this one is 7196 plus 6500, 6200 plus 6600 plus 7100 is 33. And why is that one significantly faster even though it's basically the same thing? I don't know. Divided by 5, this is going to be 67. 67. Okay, now we're going to go right here and we're going to do it again. So this is with begin transaction. We got 61, 57, that's 52, 5,000 plus 5,600. Okay, divided by 5, and we get 5520. And then same thing here. We're gonna do 6,700 plus 6,800. So you can convince AI that they're wrong. And they're actually right. Because it was right, but I convinced it that it was wrong. And this is 64. So begin transaction is for begin transaction is really only for batching inserts, because and let's look here. So yeah, without begin transaction we get 5100, with it we get 55, but in the second test, which is essentially the same thing, we got 67, and then with begin transaction we got 64. So when the batch size is only 1, it doesn't help to have begin transaction. Begin transaction is only helpful when your beginning commit, Unicode commit. It comes from batching multiple changes into a single commit. So it will batch multiple inserts into one commit more efficiently than if you were to not use begin transaction. As it said, it is like opening up a box, and if you use begin transaction beforehand, you're letting it know, like, hey, I'm about to put 10 things in this box, so leave it open, instead of like putting one item and then closing it and then opening it and closing it. And although it might be slightly faster because you're batching it in a different way, it would still be more performant than if you weren't batching it. But in this way, you're leaving the box open and you're just putting all 10 in at once. So it is like a it is a pre-warning that you're going to add multiple items at once per commit. So that is its only purpose. So I was confused here. We're not using begin transaction because we're not going to use batching. So ultimately, we got it figured out, and for whatever reason, we were actually getting skewed results with the batch version. Even when we change the batch size, that I don't know, and I don't really care about because we're not batch size. So I have been OCD and in depth enough. I don't feel like I need to go into any more depth to figure out what the issue with that was, because it was more of just some sort of programming error in the file, like something dumb. There's no thing that I'm not understanding that like giving us an 8x performance increase to the database writing system, as demonstrated by the test that we just did. So batching, SQL, not worried about it. So you can forget about that. It's so much faster than Pickle. Pickle's out the window. We're not using Pickle. So here's we're gonna go to. So we're not gonna actually use begin transaction mode. That is wrong. But we are gonna do WAL and synchronous mode set to normal. And if we remember, synchronous allows us to writing had to do with WAL mode had to do with what it's written to. It's written to a WAL file journal, which is much faster than writing to the actual database. And then synchronous being set to normal will do less frequent writes to the disk, basically batch writes to the disk instead of every single time. But it's still relatively safe. SQLite has built-in crash recovery features, and the process itself is still relatively safe and has a very small chance of resulting in data corruption. The worst case scenario, you just lose your WAL data, which, you know, I'm assuming, having not actually used it and having first-hand experience with it, but from what I read, is, you know, probably such a very minor setback. Like, and they also said that could be recovered possibly. Now, if we were going to use like a betting game, if you're going to make this to like where you can't lose data, like where it has to always have like a 100%, because then people would get like really pissed because their money's involved in this or something, which some of these card games do have those sort of features, then we probably wouldn't use the synchronous normal, because of we would want everything to be like 100% secure. Like it's like for banking. If you're doing like banking, but you're just playing a video game. If you lose like 2 seconds of data, go back 2 seconds in the game. That's nothing. No one cares. But someone got dealt a 2 and then it went back 2 seconds and now they get dealt, a 9, like, and you made a bet or something. People could get really pissed off about that. So yeah. Although that wouldn't happen because the next card would still be the next card. I think we're generally safe. I'm gonna nitpick so much. I nitpick enough. I don't want to nitpick too much. So it's a good level. It's good to be a little bit nitpicky, but not too much, because then you just, So I think what we'll do now is we're gonna disable this. This is a really good learning experience. ChatGPT and whatchamacallit help me out big mega. Let's clean this up now. So we got this 2, 3, 25 stops here. We conclusion reach much more looks like people say faster. SQLite is fast enough, and that is actually not true. That's wrong. So we'll change this because we're gonna want to look at this in the future, I'm sure. So we'll say SQLite is way faster, but Pickle is fast enough. Console the edge determine. It's true. We're gonna check shelf performance. Yeah, we're not worried about shelf. Just because SQLite's faster, there's no way that shelf could be as fast as. Shelf is gonna be slower than Pickle. So if Pickle's slower than SQL, shelf is going to be slower than SQL. So let's find a way to do this. We're not worried about SQLite dig, so we can get rid of this. Looks like SQLite is way faster. Pickle is fast enough. Note that SQLite is only faster than pickle whenever we use WAL mode. Yeah, so yeah, WAL mode. Isn't that right? Wasn't that the case? Like, let me just triple check this real quick. Let's go down here. Okay, let's get rid of that begin transaction thing real quick because we don't need it. And I guess we'll leave the batch state. So we'll just undo this to how it was before we mess with it. If we can do that. Well, you know what? I'm not worried about the batch thing. I'm going to get rid of it. So we just have full state, partial state pickle. We couldn't use full state pickle for our scenario, so we get rid of this. Then we have SQLite. Alright, so we don't need transaction. Get rid of this, the batch state, because we're not worried about it. Ooh. Okay, so then we have to modify this to... We don't have full pickle anymore, we just have partial and then SQLite batch. So we get rid of this. I need to use time it, we're not going to worry about either that. Alright, let's try to run this again. So SQLite individual is 53, and then let's check without WAL, and we have to delete it because it's still in WAL mode. Database, game state, batch, it's colon. And then partial pickle, well no, full pickle is gone, so that one won't come back. So we're gonna rerun this. So it's in delete mode, and it's set to full, and it's taking a long time. So yeah, partial pickle smokes it at this point, alright? But then, when we enable WAL mode, it's a quite different story. Now, we're at 739. If we disable WAL and do synchronous to normal, but it's still going to be in WAL mode, so I have to actually delete it again. Now it won't be in WAL mode, but normal will be the synchronous setting. It says delete for journal. And as you can see, with just normal, it's still only 209. So without anything, it's like 160. With synchronous set to normal instead of full, it goes up to 209. But then when we have WAL enabled without synchronous normal, it jumps up again to like 700. And then when we do WAL mode with normal synchronous, that's when it takes off. Bam, and then we get 4813, and in this case, SQLite smokes partial pickle. So there you go. As long as we're basically, if WAL journal mode is WAL and synchronous is normal, then we beat out pickle. So let's just make sure we note that. Whenever we use WAL mode and set synchronous mode to normal, WL journal mode. Here we go. Okay. Yeah. All right. So now we can move. What is this pathway? Okay. There we go. So we finally finished that shit. That was a nightmare. Well, it wasn't really a nightmare. We can clean up our things to do. We're not gonna do single light shit. Worry about it. Um, we learned about WAL. Is Q really necessary for Claude session to store? Oh yeah. So let's not forget about the file that Claude had made for us. Claude made us a file, and it was it had in basically its own little system, a save file system, and it was using a queue um, to hold the changes. So let's not forget about that. Um, I just add this queue for save system. Easier to remember, just like this. Remember to use suggested by Clause Q systems. Satan Claude. Satan Claudes. Santa Claude. Yeah. Saint Claude. Anyway, suggested by Claude Q. Remember to use suggested by Claude Q for save system to store data changes prior to them being written to DB as the middleman, basically, yeah. So here, can you remind me what join does? Okay, yeah. So I did want to prompt general question to 425. Prompt general question. Can you remind me what join does? Why is it needed? What join does? There you go. Pickle protocol dump. Pickle protocol is necessary since 3.8. So determine. Okay, so that I do need to take note of for when we're pickling stuff. We want to set the protocol. Dig to skeletonized classes. All right, key for save system. Okay, so the actual would be implement save system. Implement SQLite save system. There we go. So we're gonna put decided on final format for save them using SQLite WAL journal plus sync is equal to normal modes for and speeds. Replace existing in factor where we were previously. Yeah, so that's really what's next. 2.5 stopped here. Let's copy this and back over here. So we're in client refactor option 1, option 2, option 3. We use SQLite database. So yeah, we're gonna this out. We're gonna use SQL database instead. Going with new use. It says like a 354 in client refactor. No way, dude. Bam! Six, 666. Did you see it? 666. Don't lie, dude. Don't lie. You saw it. Wait, no, we didn't see it. If we just pretend like we didn't see it, it didn't happen, right? Just pretend like you didn't see it, dude. Just it didn't happen, all right? It didn't happen. Okay. 6:55 and 5:15 to 6:55. So that's an hour and 40 minutes. So we'll just say 45. So that's 1.75 plus 1.25. So that's 3, right? It's 3 total hours. That's pretty decent. 3. Okay. Cool. 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 I am on vacation, so I shouldn't even be working, dude. But I actually like coding. I like it. It's like my hobby. I like it. I skateboard, I go to the gym, and I code. And I doom scroll and watch fucking YouTube and a movie every now and then. So that is my hobby. So we're gonna do git branch. Here we go. There you have it. Secondary, which is the correct branch. We are in the correct root project directory. We're going to do git add dot to add everything. We're going to do git commit -m double quotes, paste that in. Bam, now we have our commit. 7 files changed, 125 insertions, 155 deletions. We deleted full state pickle and game state batch because we don't use those anymore. We would only have partial state and game db. And I'm going to go ahead and delete these actually because we're not like... They might confuse me into thinking they're something that they're not, so we're not going to run that test probably ever again, so we don't need those files. So then we're going to do git push canasta secondary. Now we're pushing to this remote repo, and then biggity bam biggity boom, there it goes, baby. Alright, cool. So it's pushed to the remote repo, so what we can do now is... Well, we can actually get rid of this. I mean, I'll just leave that for next time to look at, just in case I have any last-minute changes. You know how I like to change my mind, and we can juggle again. We can go back to juggling which one we're gonna do. Hopefully that's done with, and we can actually go ahead and implement this shit and get it done, because it is February. Wanted to be done with this by now. So how long will it take us to finish it? Now that we made our decision, it's gonna be that hard, man. I'm just not gonna lie. Like, that was the biggest thing, was figuring out what we were gonna use. Like CSA file JSON, we might not be using that anymore. We're probably, well, we're not. We're almost certainly not gonna use it anymore, actually. We'll leave that for next time, though. So let's close this up. We're gonna do our local backup here. Let's see. Let's go over here to programming projects. We're going into Canasta. We're gonna get the little Canasta. Go to the back up. We're backing out. We're backing up. We're deleting. We're pasting. We're going in. We're waiting. We're diving in. We're going into text devlog. Look and go to the very end of the file. There we go. 2424. That is the date of today. We go over and we can rename this to the date it was most recently dated / backed up, which was today. And that's it, guys. So there you go. We made good progress. I'm happy. We're on the road to victory. Soon we will be done with this, and I will be able to actually implement the save system in a meaningful way. And this is like big brain stuff. This is a big deal. This is allow us to. It's going to allow us to have a real, legitimate, secure system. This is like big boy type stuff. It's really not that complicated, but it's when you understand it. But yeah, that was a big milestone, learning all that stuff. Now we know what we're going with, what we're not going with. The future, we understand pickle better. We understand JSON. We understand databases generally. We understand the SQLite, some of the terms and how it works under the hood, what makes it faster, slower, secure, more secure, less secure. Yeah. So now, step is to go ahead and fully implement that and get that save system rolling. And I would say it's probably going to take a couple weeks to get the initial. I would say probably a couple weeks before the save system is about halfway done. The logic, really, I'll divide it into two parts. The easy part, which is what we've been working on, is saving the data and how we're going to save the data, what mechanism we're using, SQLite, using a database. The hard part, that should only take, like, implementing that should only take a week or two. Now, the harder part is going to be data recovery, which is where we're loading in from the save file. That is going to require some big brain determinations in, you know, checkpointing specific scenarios, like what data do we load in, what data do we not load in. You know, like, we're going to have to figure out a system for that. That's probably going to be another couple weeks, so we're looking at a month before the save system is done. But like we said, this save system is basically the last thing we're adding. This is the perfect save system. This is basically the last thing. Like, we did the menu screen, we just haven't really tested it, but this was the last thing, save system. After we're done with the save system, feature wise, not adding any more features to the game. We're going to expand it to allow for effect. That is another feature, so that's like a refactor that would probably take, I'll say, a couple more weeks on top. So we're looking at 6 weeks total for all features. We're going to do final review, play testing, that's another couple weeks, so you're looking at about 2 more months, and then by April, by my birthday, we should basically be done with this. And start looking for start putting out those applications, bro. And then, you know, we'll see. But at least to say I'm done with this major, huge, massive project. So anyway, have a good